All right, you can start now. Maybe you have to share your screen.
Yeah. So you see my screen now?
Yeah.
Okay, so my demo is very simple. So just to be create a detector and decryptor again for the new one. So this is the new picture that I have. So this is the way that the detector for the roadway and also to be the light. The lesson to be seen to go inside here is the chance for the threshold inside here to be recognized for only 2 lines. And this is the add image for the detect for the car, but I don't have a very good information inside here. So even in try to the change for the candy and also try to the change for the house line, but it's not good result. So I will be presenting the new way that I have a detect inside here later. So the building change new one and also can be recognized for the building. So this one is similar to be defined for the text one. The new, you see for the information for the candy and the side for the source to find the image gradient. So just to be changed a little bit inside the information for the candy. So the absolute size and the other things to be recognized only one. And this is the image for my cat. Also change a little bit for the candy one to recognize for the cat, but not the full one. So they just recognize for the face and also the neck. For the full one, for the body one, it not can recognize. So picture for the information. So the new one for the truck and the other things they can recognize everything based on the first one. So the feature matching. So the new one that we can have for the snack and the other one, they had the short and also the image import. This one it can recognize. Buffer fork also can recognize one because this one is exactly the same. So that's why they can recognize a lot of points. And so you can see the image here is a lot of pixels. So that's why that inside here they write a lot of light. It's not like a picture. I don't find a way to be reduce the light also. So for the plan, also try to do it and also similar with the butterfly. So I also try the new detect model. So inside here you can see the image for the car is not so good. So they cannot recognize exactly the car and the land. And that's why that I tried the new one for the detector one. This is similar with the way that we recognize the face ID in the company. So I try, wait a little bit, where is it here? So I try to use the new one, they define exactly the car inside the car, the road, and also score it. What is a car? So the one that I use is the TensorFlow and also the TensorFlow Hub. So float information inside here and detect information for the image cannot load or not. So just load the image here. So perform the object detector. So this one is the result that we can have the object image detector that we can have for the result is the key one. And identify inside here is the class is the car. So the car is the class to detector the threshold with 0.5 head and the weight for the dimension for the image like the normal one. For the E, if the number detector E1, the score to be detected for the NumPy, the class information inside, and also the box to be verified that what is the card we have. So if the score is more than detect, we define the X min, X mark, Y E, and Y min and Y mark 1 to be top, the bottom that we have. Colored to be the green one to be detect for the car, the restaurant to be the right top, the left top and right bottom to be create the restaurant, and create the email for score 2F, define it, and put the text inside to be the red for the car and also for the score inside to be recognized. So this is the result for the car detector. This one is still not good because the X head of information is exactly the car, but its had a car score is just lower, and also that it cannot define for the left car inside here because it's not full one, so they cannot define for the left corner. So that's why that it cannot write the result here. So that's why that this one is not they only recognize the full car. So but the other things that you can see that this one is very far, they just can recognize the car but cannot display inside the score. So this is the thing that still need to be improved. But because this one, I just focus to be count for the car and be detect for the car. So only one thing that we're missing is the K on the left is missing. So after that, we be just count the car based on the result for the score. So the car will be detect is 6, even that they had a 7 one. Okay, so this one is the car count and the results that we have. So I also had the other information to identify the cat. So inside the identify the cat, so you can see in the before that we just draw for the cat for the gray one. So the form for the cat one, I tried the 3 things. The first one is TensorFlow Hub also to be recognized. And the interesting here is they cannot recognize the cat. So they cannot recognize the cat one. Just to install one. So preset inside here is very similar. So they cannot recognize the cat. So that's why that I use the other model in Model Zoo to be reuse the model to translate for the detector too. So the class information is similar and also create the mask for the other things. But this one is also, it cannot use for the cat one. So they just display that no cat to be defined. So after that, I use the other one is, so you can see here, no cat is for cannot to recognize. So the detector one and also the RCDN is not recognize one. So after that, I use the CapCut. So the CapCut is mean that they will be verify the pixel of the one piece for the image to raw the information. And if the inside the outline to be recognize one segment of the cat, they can recognize this is the cat one. And just recognize again to be the information. So you can see that the cat segment will be defined under red outline. So the small pixel of the here. So you can recognize this one. And I try again for the other one, but it cannot. So this is the summary for the information to define the image inside the cat and the segmentation. So this is all the demo that I tried to research yesterday.
Okay, so you basically using the pre-trained models, right? So which model are you using exactly? So you're using Detectron or something?
I use
Yes.
detector. I use detector, and I not so upgraded. It just changed a little bit the NumPy and the other. So and also try a little bit to change this one. But after I change it, it still cannot define the information for the cat. So you can see here in no cat detection, and also inside here also no cat detection. So that's why I changed to a GraphCut. So the first one, the last one. So you can see the last one, they can recognize a little bit the pixel inside here. So they can recognize the cat here.
Mm-hmm.
So this is the three things that I try. So the last one, this one is the thing that I try to be recognize the pixel of the cats, the small
Okay.
piece of the cat here.
So the detectron models that you're using are basically for image segmentation, right?
Yeah, and also I chose the model zoo, but it's not good because
Okay.
even that I transform the R5T to the
Mm-hmm.
R101, but it still cannot recognize it.
Okay. So if you go back to the edge detections or lie detections, what did you make change on those? I mean, like the very first sections of your presentations.
The first one, the first option.
No, the very first sections of that. For example, you did some sort of features detections, edge detection, something like that. So you go up, you can go up. Go up again. Yeah, go up to the very first one. Up again. Um, yeah, in SIF detector. So in SIF SIFT.
SIFT.
You're doing SIF detector, right?
Yeah.
Okay. Just stop here. So this is one. Let me. You go to the row detection first.
The dot one, the row, right?
The road. Yeah. Here.
Yeah, this
So
one.
yeah. You go down.
Yeah, here.
Yeah.
This one,
You can go.
right?
Yeah. So this one is perfectly detect the line, right? So if you go down another image, so what is the problem with this one?
This one I don't know why it cannot. So you can see here the first one here. So you can see here a lot of line like that.
Mm-hmm.
So I cannot remove it to be here exactly only one car. So you can see here they also had a line exactly
Okay.
for the one here. So I cannot do anything. Even that I changed this one and also I changed this one, but it's
Okay.
still not to be very sharp information inside here.
Okay. All right. So what did you do in here? I mean, like, what are the steps that you did before you draw the line? Can you explain this block of code?
So the information inside here, the first one that the road line, the road row, and also I changed to the gray one. And I changed the information inside the Kenny to be right the act one, like that. Change the information here to be a little bit before, like, so you can see the rod here. I just changed the information inside the Kenny, so the line is correct. But inside this one, I changed it, but it's still not the correct one. And also I changed this one. I know this one I don't change. So I just only change the Kenny one and the line one.
Okay.
Yeah.
I see. So you basically using canny edge detections to first detect the edge,
Yeah, it's
and
correct.
then you use half to connect all the detected edges to construct the line, right?
Yeah, it's correct.
Okay. I see. All
But
right.
yeah, this one is not understandable, so I still find a way to understand it because with the demo one, you can see the two image is very similar, but don't know why that this one is not run. So that's why that I still find a way to use it.
Okay, sure. All right. Um, okay. Thank you.
Okay.
All right. So, who is next?
Teacher, I would like to present.
Okay, sure. Please go ahead.
Yeah. Hello teacher, do you see your ring, my ring?
Yeah, sure.
I would like to demo vision computer vision application real-time image filtering, geometric transformation, and panorama reaction. I would like to introduction. This project là interactive computer vision demonstration using a webcam. It highlight how real-time visual data can be processed using Python and OpenCV library. Application is designed with intuitive keyboard interface and dynamic on-screen feedback. It's showcase practical implementation in real image filtering, generated information, and visualization. I would like to show you after picture overview, core lab, computer vision demo, and capture at on mod and UI Lewis, library, OpenCV, real-time computer vision operation, NumPy, numerical array operation for image manipulation, OS file and system level integration. Major component camera interface capture and measure like webcam face model handle several logic for its operation mode. Structured by dynamic UI for filter and transformation control. Apply chamfer engine for caption and rotation and transition. Panorama picture combine multiple image using OpenCV Twitter API. I would like to show you user interface and control. Key N normal functionality, normal mode, app filter mode, C geometry mode, B panorama mode, C capture for panorama, S switch panorama, 0, 2, 4 filter selection, D top debug mode, Q which for filter mode enable user to apply various visual effect in real time. 0, none. Original video fit. 1, right retrieve convert image to monochromatic. 2, browsing less smooth image to reduce noise. 3, can detection highlight X using USB random detection. 4, randomness adjustment in or degree image randomness. Interactive trackbar so fine tuning of parameter. For geometry mode, allow real-time manipulation of image geometry, rotation, rotate around image center using angel trackbar, selection shift image along X and X using separate trackbar, Kelvin zoom in or zoom out. We are and Kelvin factor trackbar. On transition apply using a single apply function support adaptive visual feedback and aberration detection. For Banana Mods, enable user to create white and wheel by switching multiple images, capture red KC to capture a frame from left to right, which red S to combine capture frame into seamless panorama. You utilize often CV adapted with module with feature detection and alignment. The final result is delay and save it at panorama result GBC. I would like to highlight and benefit in interactive learning tool. The idea for demonstration financial computer vision concept, real-time processing, instant feedback, enhance user experience and implementation, model architecture, easy to maintain and custom for new feature. Practical application suitable cho asynchronous demo, prototyping, and vision by UI development. I want to demo lead the demo detection never row it mod using keyboard command interact with real-time filter zero vision and variation. I would like to, I would like to do you see Rain my score?
Yeah.
Okay. I would like to demo. Do you see my Rain? Okay. And K N no more. Q which G Angel rồi email tránh sân ads scale zoom out zoom in app filter zero none one right hai number two number three cái này red filter red number four red Ranet review Ranet Inri Ranet B banana now I touch email room left to right C capture email I would like to say if you say read say so if you say that I wrote it my read
Yeah.
number set. Someone, yeah. I know X. So banana X, yeah. X. I would like to show you emails. Yeah. Banana result emails. I would use show you. Hello teacher.
Okay.
Banana email. Yeah.
Okay.
Okay,
That's
thank you.
okay. That looks good. So for panorama stitchings, what functions do you use for the final result? Are you using the pre-built function for panorama stitchings, or you're using the one that customized you write it yourself? Which function do you use for panorama stitching?
I would like give you your support. Yeah. Yeah.
Okay.
Thank
I
you.
see. Okay.
Thank you, teacher. Yeah.
All right. Thank you.
Okay, thank you, teacher. Yeah. Cảm ơn, thank you. Yeah.
All right. Who is next?
That's me.
Okay. Then go ahead.
Hello, teacher. Do you see my share screen?
Yeah.
Yes. I made a simple project about place an AR sphere using AR UCO and OpenCV. So the idea is detect AR UCO marker using a webcam, my webcam, then estimate camera position related to the marker, and the next step is render a 3D sphere above the marker and visualize. So the step I took 6 steps. The step one, in step one, I capture video frames using my webcam. Step two is detect the markers in the image. Step three, estimate pole to using SON PNP to detect vector rotation vector and translation vector. Step 4, I create 3D point. Here is a center of sphere onto the image. Step 5, I draw I draw a shaded circle to simulate the 3D sphere. And step 6 is overlaying result on a live camera feed. Here I use OpenCV to for computer vision computation. I use NumPy for calculate for numeric calculate and magic operation, and I use CV2 AI UCO to make to detect the marker and pose and estimate pose. So there are some important parameters I use. The first is camera magic to configure the camera magic, the focal length, optical center. The second is this distance coefficient to about the lens distortion. The third is model points is used for AR UCO marker to identify a corner. the first is sphere center 3D to locate the sphere on the center of the plane, and I use rotation vector and translation vector from Son PNP function. So from that I can draw the marker borders on image and render 3D sphere using 2D setting function, and I can display in real time using OpenCV window. So this is the result. Then I can demo my code. Can you see my screen now?
Yeah, yeah.
So when I
We don't see the app screen, so you might have to move it to this screen.
Can you see now?
Yeah, yeah.
Yes, I use the UCO marker. I can here I can put the I can place the 3D sphere, and I can identify corner of the marker here.
Okay. So but before in your slide you say that you have to calibrate the cameras. So how do you get the data calibrations done? So how do you, how did you get those like camera intrinsic matrix, something like that? So yeah, how did you get those matrix from?
Here I you here you can see in my screen it is parameter to calibrate my camera about focal length. Focal length for this is I set up for my webcam in this resolution here.
Okay. Okay, so you basically just hard coded the camera metrics, right? So you didn't do like the calibration. You just assume that you already have these metrics, right?
Yes.
Okay, okay. And then you draw a sphere. So it's a 2D or 3D sphere.
It's the 3D looking spheres. I have a option to make a set to show like simulate the 3D sphere. Yeah, I have I make a shadow so it look like 3D sphere.
Okay. Oh, okay, okay, I see. I see. All right.
Thank you, Professor.
Okay. All right, all right, all right. Okay. So thank you. So who else haven't have a presentation yet? I think we are missing two, right? We're missing two. Anyone else? Let me see. So we have Palm Quack. Hung. I'm not sure I'm spelling the name correctly. So I think yeah. So I think you haven't present, right?
Yes, I can present it,
Okay.
but I'm failed to start the video camera. Wait a minute.
Mhm.
So I cannot open the webcam camera,
Okay.
maybe because of my project.
Mm-hmm.
So what happened? Oh, it's because of my project. Okay. I have to close the app. Okay, so let's do it.
Yeah, maybe if you have any like presentations
I
or the code, maybe you can walk us through that. Yeah.
here. So can you see my screen right now?
Yeah.
Okay.
Yeah.
Okay. So this is my so I would like to present my project first, and then after that I will have to turn off the my webcam to demo it. Otherwise, it would be may have an error like you can see. So my project is about Air Panther. So before I present my project, I will let you guys watch a video to see an application of it that we can use in real life. So this is presentation of it. So we are in a surgery room. So basically, what I just showed you is that situation that you guys can have an imagination about my project and what it can do in practice. So basically, in a surgery room, if a doctor with their hand, of course, has been sterilized, and then they cannot, but they have to show their assistant something. So they cannot touch anything. They cannot touch the keyboards. They cannot touch anything. So they have an application that you can use a point pen like this, or a point of like cherry tools to show that your assistant what to do. So basically, I am just trying to demo like a very foundation step. My project is a presentation of a very foundation step of this application, and I call it like Air Panther. So this is how it can be applicable in practice. So basically, I try to let me put it here. So basically, the project is that like I said, to create a virtual painter that allow user to draw on screen by simply moving a color subject. In this case, I chose blue in front of webcam. So I also use Python and OpenCV library. So I also have 6 steps like the lecture that you have our professor have taught in our class. So I also do the image acquisition, which the machine can see it, and then I do the image processing, which I apply some of the Gaussian which we have learned in class, and also the segmentation, the feature detection, and object recognition, and finally I piece everything together into the picture, and we call it scene understanding. So let's go into the first one. The first one is very simple, and it's just image acquisition. It's as simple as it is. So I just read the image from the camera, easy, there's nothing to see. And the second step is about the image processing. I'm sorry for the Canva, but I tried to put the code, but you see, what I tried to demo it before I showing to demo, but I would like to explain something. So in this in the code behind the presentation, I have there's I try to process image by using the Gaussian, and as in your I read in your slide, the rule is the standard k equal to standard deviation, and when I try to set it very small, like 11, as if my memory serve it right, because I don't have the code here. So, and it can you know, like the noise like you see is a lot, and the picture in below, but the picture above I set it like to 151, so it's very large, and so it's consider the whole screen of my screen as the whole picture, as a whole, in as you can see in the mask here, you can see the whole picture, but it's very slow, so I have to choose the balance number for the image processing. And at the same time like because the problem is also about the lighting, because when the light is changing, the color of the pants also changing. So another step of image processing. I'm sorry, because the image have you know, like cover the code, so I have to remember it by my memory. So I have to change it into HSV, because the RGB is heavily impacted by the light, because whenever the light change, the code will change dramatically. So I have to also change to HSV. So that's the two steps that I use to do the image processing. After that, I also try to do some segmentation and do some in order to do the segmentation. I also try to let the machine don't confuse between the smaller dot in my screen. So I have two functions. I use two functions. It's called dilute and erode. If my memory serves me right, if I try to choose the, I tried to do the, I try to put it at the parameters equal number 2, because, and this is just the two different scenarios. I try to increase it to a very extreme, so you can see that this effect. So in the picture above, if I try, I try to increase the function of erode into 100, so you can see that it's already like erase all of the mask. This cannot detect anything. And the first picture, I increase the parameter of the code dilute, so it can like exaggerate the color, so you can see like it's considered the whole screen as white as in the masking. So after I do the segmentation and I do the feature detection, so basically here very luckily that I don't put any image here, so I can see the code. So you see the contour is like the treasure. I consider as treasure. So basically this is, I try to recognize all the treasure, all the things that maybe that the object I'm trying to draw. And after that, I if you know, like I find any in my treasure, if the treasure, I will see equal max contours, mean that I will pick the biggest treasure. I will pick the object that have the largest area in my screen, and then I try to find the the position of it, and try to know the position of it, and finally after that, and then I recognize the circle of the object, because when you put the object in the phone screen, it can be sometimes it can be it can be not very rounded. It can be like have changing a lot. So I have to draw a circle around it, and so I can so I can find the center of the contour, and then finally I just put it into an array, and draw on the screen. So now I would like to demo my code, and at the same time I would like to work through some of my code, and then I will present my the final slide later. So if I have to turn off my camera right now to turn on my app. No. Okay, good to go. So this is me right now. I'm in the pagoda. So let's try something here. So you can see when the text screen, and then I can draw. I'm sorry that I don't have a pen here, but if I have a pen here, I can draw it. You can see I can draw it here. But and if, like I said, I change this into let's see 2 standard deviation. I change it to 165. Let's do it. And you can see that it's very slow. It's very slow. And at the same time, it consider the whole thing as one object, because I already erased all the noise. So that.
So what it is tracking? It is tracking the middle color of the template, right?
Right. But basically, if I have a pen here,
Okay.
a blue pen here, it would be like only one object. But this is just, I want to have a lot of thing here, so people can see that it can have a lot of noise, and how we can use it, how we can still use the code to remove the noise.
So it basically tracking the blue color, right?
Yeah, tracking. But we can change. I can change into any color I want. I just need to take a picture, and then I just need to change the code a little bit.
Okay, so and in your applications, I saw there's a control bar. So what are those controls doing?
The control, what the control is doing is that it changed the color of my pen. So here, wait me a minute. So here, for example, like I don't like, let's see, that be red. Okay, and then it will be red. No green anymore.
Okay.
Yeah. So this is like red. And this is like also to me is to remove the noise. So as I see, this is to do the masking. So if I increase it to, let's say I try to increase let's say 10 times, let's say 100 times, because I want to go to extreme. See, So it will remove all the mask. So now it cannot recognize anything. Yeah.
So what if I have two blue? Right? What if I have two blue? What is going to detect? For example, I have two blue here. Which one it is going to detect?
If you have two blue, I think that the blue have larger, the blue that you put it first, the blue that you put it in front of your screen, so it have larger area, and that the first that it will recognize. But if the two blue equal and the Gaussian is not too large, I think it would recognize the blue that have the color that exact the color that I have a new color that I set here.
Yeah, so how is that conditions? How do you make that logics? Whether if you have two blue, which one it is going to choose?
I think if I try to follow my initial path, which I try to be useful in a surgery room, logically, I think that I would choose the I would choose the blue that near the screen. I think we'll know more everyone. I would choose the blue near the screen. That near the webcam.
I think what you do is that you show your screen again. Your image of blue is kind of conservative because it have a range of blue, right? So it makes sure that whatever blue you want, your application can find a blue that suitable to the blue that you set. So for question of Dr. Shah, I guess that you can add one more function to detect what is the blue you want. For example, when you show your screen and you bring your blue pencil in that area, and that function can help you to detect the color of that blue, and then use that blue for the other step.
I cannot, of course, I cannot increase the Gaussian. So it's mixed two blue together, right? Because that's not correct. Because that would be, for example, like two blue. I'm sorry, let me turn on my screen. So I turn on my webcam. So if I two blue like this, so I don't like it to, because of the Gaussian, it choose the middle right here, right? Because it would confuse if the surgery had, yeah. I think I would like, I would agree with the methodology that it have to consider the exact blue to go with.
Okay. All right. All right. So this is it, right? For your demo.
Yeah. This
Okay.
is,
All right. All right. Thank you.
okay.
Okay, so I think we're missing one student. I'm not sure he or she joined the class or not. Yeah.
It's not in the Zoom.
He
Hey,
have need work, so he send mail for you to delay schedule next week.
Okay.
Hey, Professor, actually, like, I have several projects, another mini project. So if you can, in next week, I would like to present one more. Yeah, with to take advantage of the opportunity that one of my classmates have just delayed the schedule.
All right, sure, no problem. Yeah. All right, so which means that we probably have two more presentation next week, not next week, the week after that, in which we are going, so we are going to do that presentation live from Hanoi. All right, so because I will be visiting Hanoi on July 12th and 13th. All right, so the last presentation will be on site, apart from Mr. Pham Quoc Hong. So which I believe you will be online, right? So yeah. So for I'm not sure for Mr. Nguyen Huong Wet. So he will be doing on-site presentations. Okay. All right. So maybe this is it. So all right. So let me just share this first. All right, there's a couple of announcements before we begin with the rest of the class. First, please submit your code, your presentations, or any resources that you want me to look at in this Teal. All right, so you can go down to these submissions, okay, and then you just submit your resources like presentation file, any file. So currently, I saw only 5 submissions, 5 out of 9. So please don't forget to submit this. All right. And also for the final presentations, not final presentation, final project, all right, for the course project. As I mentioned in the first class that you need another project as a final project in which you don't have to present, but you need to submit a report, all right? And for the report, you will follow the IEEE template. So you can get the template from here. So I'll send you the link later. So the template would look a little bit something like this, all right? And then the topics or the sections within the papers would be, for example, introductions, literature reviews, methodologies, experiments, conclusions, and reference, right? So these are the mainly require 6 sections within the reports. All right, I'll send you the detail later. So I will post the informations about the final in this Teal. Yeah, you can check it out later. All right, and for the final projects, you are free to choose the topics under this computer vision class that you like. And it shouldn't be like you just grabbing some models, some pre-trained models, and then trying to run it. That is not like that. So what you have to do is to enhance it to in some way, right? You have to enhance it. For example, you have some sort of you have some of your own data set, and then you can grab the existing models and then you fine tune it on your data set. All right, and so then that's okay. But if you're just using the fine tune model and then trying to feed some data in and then get some results, so that's not allowed. All right, you have to amend, or you have to add something to the workflow so that you can write some report. What is your contributions? What you are trying to customize the applications. All right, so that's how you have to do it. Okay. So any questions for the final projects?
Question.
Yeah.
Most likely, I mean, the data sets we have enhanced. I think is it about image or video? I don't know. The source, so we can grab from the internet and then, or just create by our own data sets.
You can grab any data set from the public data set and then trying to come up with so I am very sure, or I am very certain that not all the models that run on all data set that publicly available. So you might probably need to grab, for example, you grab a ResNet and then run it on some public data set, and
Yes.
then see whether you are trying to fine tune something, you are trying to customize the models, you are trying to fine tune with some sort of unfreezing some of the weights or some of the parameters of the model, something like that. So those are to give you a practical hand-on experience, and then trying to come up with your idea what you want to do. For example, you might probably interested in using the models with healthcare in the healthcare area, right? For example, detect some cancer within the medical images, something like that. So you would probably run some of the models with a public available medical images, and then trying to come up with some custom workflow, because in training loop there are many things you have to do. For example, trying to fine tune it, trying to change the model, trying to do different data augmentation, something like that. So there are lots of things you can do. All right.
Yeah.
And then you probably need to explain why you're choosing these models over the other, something like that. So basically, in the reports, you have to write the 6 mandatory topics in the papers. All right. Any other questions, or the resources that you can grab the data would be, you can go to for example, Kaggle. In Kaggle there are tons of data sets you can use. So you can use those from those data sets as well, no problems. Okay.
Okay, thank you.
Okay. All right, so I'll post the informations on Teal. So I'll make it in the announcement sections and about the final projects. Okay, I'll post that later today. Okay. All right. If no further questions, so let's start. So let's start with our today lecture. All right, so today lecture, we are going to begin our journey in object detections. So we will have 2 lectures for object detections. All right, so today, the first one and the next lecture will be in Hanoi about object detections. All right. So today we are going to discuss about the regions-based CNNs or RCNNs for object detection task. All right, and then we will also learn about cropping features. For example, ROI pools, what is ROI aligned, and then we'll also discuss about fast RCNNs, IOU, and MAP matrices. All right, so how can we measure the performance of the object detection models. All right. So if so far we have been discussing about the image classification, right? So we have been discussing about linear classifier for image classifications, and we also discuss about the CNN, so that we can use those models to classify the object within the image, whether this entire image belong to which categories of our interest. All right. However, if we look at the computer vision tasks, there are many tasks that we can do. All right. So what we have done is the classification task, in which we want to we want the answer from the model whether this entire image belong to which category. So there is no spatial extent, which means we don't want any information about locations of the objects within the image, but we just want to know what is in the image. All right. But there are many other tasks. For example, semantic segmentations. That is, we don't care about the objects, but we just care about the pixel. What are which each pixel belong to which category. So that's the segmentations. We will discuss about this as well. and also the objects detections and instance segmentation. So these are the tasks that we are interested in detecting multiple objects within the image. All right, so today we are going to first discuss about the object detection task. That is, we are interested in detecting not only the objects, but where it is in the image. All right, so the task definitions of object detection is that let's say that we have a single RGB image, and then the output that we want is a set of detected objects. All right. So for each objects, we want to predict two things, right? For each object. So first, we want to predict labels or category labels from a fixed and set of unknown categories. For example, in our data set, we want to detect the cat, the dog, the elephants, the pig, the bird. So these are the fixed set of categories that we want to predict. And also for each object, we are not only want to the answer only want, we don't want the model to tell us only what is in the image, what are in the image, what objects are in the image. What we want to know, what are in the image and where they are. All right, so that is we want to know the bounding box, right, of the locations of the object that has been detected. So the bounding box can be represented with 4 numbers, that is xy, which is the center of the bounding box, and the width and the height of the bounding box. So these are the informations that we require the models to give us. All right, so that's the definitions of object detections, the task object detections. And when we are doing object detections, we might face some challenges. For example, there could be multiple outputs, so there need to be multiple variables or the numbers of objects within the image. All right, so there probably be many dogs in the image. There probably be many cats within the image, and then we also need to deal with multiple types of output. For example, we need to predict what is in the image and where it is. All right, what objects are in the image, and then where are they? Where are they? So those are the multiple types of input. And basically, the challenge for object detections is about the large image. All right, since we need to localize the object. So for some reasons, the low resolution image might not work very well, might not give us the best performance that we need. So we might need a higher resolutions for detection task. Let's say like it often use like 800 by 600 pixel resolutions. So if you compare the resolution to classifications, it's roughly about 2 to 3 times larger than the image classification task. All right. So when we increase the resolutions for the input, so that means the computational resources that is required for detection task would proportionally goes up with the resolutions of the image. All right, so these are the challenges when we are performing the object detection task. All right, so let's first look at how can we detect the object. So let's first take detecting a single objects, right? For example, we have the image of the cat, and then we pass it into some network. For example, it could probably be AlexNet, ResNet, something like that. And then at the end of this one, we would probably have a linear classifiers or a fully connected layer, right? And we have another fully connected layer here that is mapping a vectors of 4,000 to 1,000. That is for example, we are detecting the objects using ImageNet dataset that has 1,000 categories. So if we feed it in, and then we want to detect what kind of objects are in this image. So we just pass a vectors of 4,000. That is the last layers of AlexNet into another fully connected layers. So that is mapping from 4,000 to 1,000 to match with our class. So what we get is the class score of each categories. So this is how we predict what is in the image. All right. So we can measure the performance using softmax loss. All right. And then another thing that we need to do is we need to also find where is the objects. All right. So we find what, and also we need to find where. So what we can do is that we probably need another fully connected layers, separate fully connected layers to mapping from 4,000 dimension to 4. So that give us the box or the bounding box coordinates, that is X, Y, W, and H. So this is give us where or the locations of the object within the image. All right. So, and then this kind of task, we would probably use L2 loss to measure the performance of the models. All right. And since we need to perform during a training, we need to perform a back propagation to update the weight, so that we need to combine these two weights into a single loss value, so that we can use that as a representations of the entire model loss. So then we can perform a back propagations, calculating a gradient, and then update the weight. So we might need to probably use a weighted sum so that we can get a final single loss value for gradient descent or back propagations. All right. So like I mentioned here, these sections of the model would be probably we can use a pre-trained models in ImageNet, and then the loss value would be a multitask loss, for example. All right. So the problem here is that image can have more than one object. All right. So the example here is just one object, that is a cat. But what if in this image we have multiple cats, or we have a cat and a dog? So how can we address such a problem? Okay. So in order to perform this one, we need a different number of output per image. All right. For example, if we have a single objects within the image, we probably need 4 numbers to give a localizations of the image, right? 4 number is the bounding box information, that is the middle of the bounding box, width and height of the bounding box, right? And if we have this like 3 dogs, 2 dogs and 1 cat, we need more numbers to represent the locations of these objects. But let's say that we have many dogs, we have duck, and then we want the model to detect each and every dogs within the image. We need many numbers to represent the locations of the objects within the image. So which means that the output that we requires from the models is not just the number of class, but it's including the locations of the bounding box as well. All right. And then in one image, the number of objects varies, so as the number of the bounding box can also vary. So this number at the end would be also vary. So we need to handle such a problem as well. All right. So this brings us to the first techniques that we can use to detect multiple objects. Right. So let me just pause here. Any questions so far? All right. So if no questions, so I think we can pause here for 10 minutes break and then come back. We'll discuss more about the first technique that we can use to detect multiple objects within the image by using the technique called sliding windows. All right, so let's come back at 10:30. Is everyone back? Yeah, probably I can assume everyone is back. All right, so let's start it. Let's get started. So let's get started with the sliding windows, right? So this is gonna be our first methods. How can we detect the multiple objects within the image, right? So first, the sliding window. So what does this do? So we probably the first technique that we can use, it could be very brute force or very heuristic. That is, we probably have a crop sections of the image, like sliding the window, these blue windows, we sliding across the image so that we're gonna get a crop image, and then we feed that sections or the cropped image into the models like CNN, right? And then we want the models to detect whether in that particular cropped image contains any objects or not. It's either a cat, a dog, or it is a background. All right. For example, if we have these windows or cropped image and then feed it in the models, so we would expect the models to detect that is a background. All right, so there's no cat or dog within that image. And then if we some sort of sliding the windows and then getting this area of the image and then crop it and feed it into the models. So we're expecting that the model would detect a dog within these regions of the image. So, and then we sliding another windows again, and then feed it in. It should be a dog within that particular crop area, right? So the problem here is that there are how many possible boxes are there in the image, in this image of side H and W, right? So we can say we can see that a possible X positions, that is the width of the image, and a possible Y positions can be this number, right? So if we take that combinations out, so we can see that we can end up with this many numbers of boxes that are possible, that if we sliding the windows. So if we look at this image, for example, it has a resolution of 800 by 600 pixel, right? So there are roughly about 58 million boxes that can exist in this image itself. So there's no way we can evaluate them all, right? So 58 of them, and then trying to feed it into the models, and then trying to come to see whether which box contains what objects, and then so that we can localize the objects as well as detect the objects at the same time. So by using these techniques, we need to apply CNN to a huge number of locations, scale, aspect ratio, right? So that's very computationally expensive to do this kind of object detections. All right. So that's bring us to the concept called regions proposal methods, right? So in region proposal method, there's a very famous technique we call a selective search. All right. So this technique, what does this technique do is that it just find a blobby image regions, right? That look like that's likely to contain some image. So you can use the technique to detect anything. Probably it can use something like edge detection, corner detections, and then combine them together between different image. Or we probably can use a sift technique to find whether which location most likely or likely to contain any objects, and then we just crop that region. And then this is what the selective search is trying to do, right? And then this technique run relatively fast to find some sort of potential regions within the image that would likely to contain any object. So by using this algorithm or this technique, it will return us roughly about 2,000 region proposals in a few seconds on our CPU, right? So if you compare with the sliding windows, right? Sliding window, we probably have roughly about 58 million possible windows with different size, with different aspect ratio, right? So by using this method, we can reduce to 2,000. So, and then it can run very fast. And that's bring us to the first models, very classic models, right? That is called region-based CNN. So what it does is that, let's say that we have this input image, and then we ran this region proposals on this input image, all right? And this this is what we call regions of interest from proposal methods. So it will return roughly about 2,000 regions, right? 2,000 regions. And then we warp this image, right? We warp this image to some certain site, for example, 224 by 224. So we warp it, right? Because a region proposal or our region of interest, it could be in different size, right? But our CNN model requires a fixed size input, right? So that's why we need to warp it. We need to warp the image into a certain size that is called, for example, 224 by 224, something like that. And then we feed that into a COVNET or CNN, all right? We pass that to. So the models will have to classify each regions, each proposal regions or region of interest that we pass it through. It needs to classify whether that particular regions contain any objects or not, all right? And not only that, we also want the models to tell us the bounding box, all right? But in this case, the models does not tell us exactly where is the bounding box, all right? It just tells us the transform or the translations of the box, which means the difference between the ground truth and the predicted box, all right? How much errors from there. All right, so that's what it predict the transformations in X, Y, width, and height. All right, so let's see example. All right, so we call this task box regressions. All right, we call this task box regression. So let's consider this region proposal. All right, let's consider this region proposal. It had a center as PX and PY with PW width and then with the height of PH. So what the model is doing is it is going to predict a transform T of X, T of Y, T of W, T of H to correct the region's proposal. What does that mean? That means that this is the region proposal, right? This is the region proposal. So the output box can be defined by using this formula. All right. So what we want to get is that we want to get the output box, right? We want to get the output box. So we can find the output box by using these transformations. All right. So these transformations, the model is predicting this. And then we perform this mathematics, all right? For example, if we want to get the predicted bounding box center, we could use PFX plus PW multiplied with TX, so that we're gonna get these new centers of the bounding box. This is the output bounding box, which is the predicted one. All right. So the thing that the model is predict is the blue one is the ground truth, right? The blue one is the ground truth, and the output one is this one. So what we want to do is we want to minimize this transformation to be as close as to the ground truth. All right, but this is what the model is trying to predict. All right, and then this sort of transformation is scale and translation invariant as well. So because the CNN doesn't see the absolute position, so that's why we just want to find the errors between the predicted bounding box and the ground truth only. All right. So so if we give the region proposals and the target output, so we can solve for the transform of the network, so that we can get this value back. So how large the area is. All right. So how this model is being trained. All right. For example, before you're training the object detection models, you have to label the image, right? So this is, for example, this is one of your input image. So, and then you're just labeling this each of the box, trying to perform the box. So this is what we call a ground truth box, right? And then you run this image with a region proposal method. So probably, for example, the bright blue here is the region, the resulted box that you get from a region proposal methods. All right. And then you are trying to categorize each region proposal as positive, negative, or neutral based on the overlapping with the ground truth box. All right. So to categorize these regions to either positive, negative, or neutrals, we are going to use the matrix called IOU. All right. We are trying to find the overlapping regions between the region proposals and the ground truth, right? So that's what we are trying to categorize that. But how is the IOU works? All right. So by comparing the box, right? The IOU is stand for intersections over unions. All right. So we are going to use this to compare between the ground truth and the predictions of the models. So let's say, for example, the green box is our ground truth and the blue box is our predictions. So to calculate the IOU, we first find the area of intersection, that is this orange area, all right? And then we divided that with the areas, with the union areas of our ground truth and our predictions, that is the purple area over here. So that's what we got the IOU, right? So if the IOU roughly about 0.5, that is 50%. So we call that as a descent. And if the IOU kind of greater than 0.7, that could be very, very high overlapping. So we call that pretty good. And if the IOU is like greater than 0.9, it would be almost perfect, all right? And in the reality, you will never get IOU equal to 1. No way you can get IOU equal to 1. So 0.9 is almost perfect. That is like pretty much we can get from the models. So this is how we calculate the IOU and then compare the predictions with the ground truth. All right. So after we categorize the regions, the region proposal with the ground truth, all right, we categorize them either positive or negative or neutral, all right. So then we crop it, the pixel from a positive and negative regions only, right? Because from here we have many region proposal, right? From region proposal methods, we can get roughly about 2,000 regions, all right? From that 2,000 regions, we need to label them or categorize them by using the IOU, whether which one is positive, which means that it is most likely overlap with the ground truth. And also we need to categorize them as a negative, which means that it's unlikely to overlap with the ground truth. All right, so we're trying to categorize the regions proposal with the ground truth first, and then we crop only the pixel from the positive and negative proposal, right? So the positive will be dark blue and the negative will be red over here. So we crop only the pixel from these regions and then resize it to 224 by 224. All right. And then we feed these each regions to the CNN models. It could be AlexNet or it could be ResNet. All right. And then for the positive regions, we need the model to predict both the class and the transform. That is TX, TY, and TW and TH. Right. And for the negative one, we just need the model to classify just for the objects, whether it belongs to which one. So the negative one have to be predicted as a background. All right, so it should be predicted as a background. If it predicted as some other object, that would give a penalties for that. Right. So that's how you train it, right? You keep doing it. You keep training this. For each image, you perform a region proposal, and then for each regions that you get from the region proposal method, you categorize them into either positive or negative, and then crop that positive and negative only. So you don't take a neutral one, positive and negative. You crop it, resize it into 224 by 224, and then feed these regions into CNN models. All right. So the models have to predict a class and a box locations or the bounding box. So you keep repeating this and then also adjusting the parameters of the model as well, because we have a ground truth. We know how to measure the classification predictions, and then we know how to measure the difference between the predicted box and the ground truth box. All right. So we keep repeating that. But so after we finish training at test time, so which means inference, so we did the same thing. We run a region proposal method. So we probably get like 2,000 region proposal. So we resize it again to 224 by 224 and run each regions into the CNN models. So we're gonna get a class score plus a transformations. All right, plus the transformations of the bounding box. All right, and then we can threshold whether which one we want to select and to a correct one, because the models can predict, right? For each region, the models can predict, can give us a probability whether that regions belong to which card. It could be a dog, it could be a cat or not. So that's what we get from each region. So we set a threshold whether each region, if it has a probability greater than some threshold, let's say 0.8, all right, 0.8, we are going to keep that regions. We are going to keep that region, and then we'll take that region as a predictions of that particular objects. All right, so then we know that regions within the image, we know that this region within the image is the dog and the locations of the dog as well. All right. So the problem is that, for example, for this dog, for these golden retriever dogs, right, there are two boxes over here. So, and CNN models, right, CNN models can probably be correctly predicted that these two boxes belong to a dog category, right? So which means that these two boxes overlap. But for these objects, so from our sense, it should be just one box, right? To classify as these regions as a dog. But we get these two boxes. So how can we eliminate that overlapping box? And then another problem is, how can we set this threshold, right? How can we set this threshold, whether which region to keep and then which region to throw away? All right. So to deal with problems of overlapping box, all right? So what we can do is that first, we can use the method called non-maximum suppressions. I hope you remember this name from the edge detection. So we heard this before. So the solution to this problem is we can do a post process raw detection using non-maximum suppressions, or NMS. All right. So let's take this as an example. All right. So for this image, we have four regions that are overlapping with each other, right? We have this, and then each region, it has a probability of the predictions that the model gives us, right? For example, the region, the blue region here, the model gives the probability of this region being a dog is 0.9. And for these orange regions, the models give a probability of that these regions belong to the dog 0.8, all right, and so on. So how do we do the non-maximum suppressions is that first, we select the highest scoring box, all right? From this example, it would be this blue box, right? Out of these four boxes, the blue box has the highest score, right? Because it has 0.9. So first we select that one. And then we eliminate the lower scoring box with IOU greater than some threshold. All right, we eliminating the box. So what do I mean by this, right? The lowering score is this box. So what we are going to do is that we are going to find the overlapping. We are going to find the overlapping between the blue and the rest of the box, the rest of the regions. All right. For example, we are finding the overlapping between blue and orange, the overlapping between blue and the purple here, and we are finding the IOU between the blue regions with the yellow regions here. So what we are going to eliminate is that we are going to eliminate the overlapping area that has the highest score among the rest, which means that we are going to eliminate the orange box over here because it has a high IOU with these blue regions. So we are going to eliminate that. All right. So if any box remaining, which means that correct, now we are having the purple and yellow box left. So we are repeating the same process. Okay. So we are repeating the same process, that is, we select the next highest one. So out of these three regions, that is blue, we are already done with that. The next highest score will be the purple one, right? Because it has the probability of 0.75 being a dog, but the yellow one would be 0.7. So we select the purple regions, and then we repeat the same thing. We try to find the overlapping regions of the purple with the yellow, right? And then it is greater than the threshold that we set, which is 0.74. So we eliminate the yellow one. So that's how we perform a non-maximum suppressions with the overlapping boxes. All right. So at the end, we will have with just two boxes that is the locations of different dogs within the image. Okay. So you guys got the idea with this?
Yeah, clear. Thank you.
Okay. So but there are some challenges that is left unsolved currently. Is that, for example, in this image, there are multiple similar objects within the image, and then there could be multiple overlapping regions, right? If we run the object detection from here, so it could be many overlapping regions. So if we are using NMS here, it would eliminate many good box from here. So there's no good solution yet. So it is just another research topic that has to be solved. Okay. So so now we know how the models make a predictions, right? We know how the model make prediction. So the next question is, how can we measure the performance of the model itself? All right, how can we measure whether how good it is the models, how good is the predictions of the models for each particular objects that we are interested in? So that's bring us to the evaluating object detector. By using a mean average precisions, or MAP. So how does that work? So when you are going to evaluating the performance of the model, you are going to run it with a test data set, right? So you run the object detectors on all test set, on our test image, and then you perform the NMS, which means that you are trying to eliminate the overlapping boxes, all right? And then for each category, you are going to compute the average precisions, which is equal to the area under precision recall curve. So how does that work? So let's say that these are the test image that we have. All right, these are the test image that we have, and then we pass this image to object detectors, and then we perform the NMS. This is a result we got. The blue box is the result resulted from the models, right? From the object detector after performing NMS. All right. So what we are going to do is, for each category, let's say that in these models, we are interested in only two objects, that is cat and dog. All right. So we are going to evaluate the models for each category. For example, here we will first evaluate the models precisions with a dog categories. So what we are going to do first, after we get this result, we are going to sort. We are going to sort all the dogs detections by score. So for example, these four images, we are going to sort the value or the score of each dog, the box that is predicted as dog in these four images. All right, we are going to sort them, because the score is the probability that each region, the models guess that there will be a dog in that region. All right. So we sort the score. We sort the score here, and then for each and every image, we have our ground truth, right? We know where is our dog is within this test image. We have the ground truth. So what we are going to do is that for each detected regions, or each detected one, we have already sorted the highest score to lowest score. So if it is matched with some of the ground truth, and that match have the IOU greater than 0.5, if that match have the IOU greater than 0.5, we will mark it as a positive and eliminate the matched ground truth. All right. For example, this first region that has the highest score, that has the highest prediction score, it match with this ground truth, and then it has the IOU greater than 0.5. We mark this as a positive, and then we eliminate this ground truth from our ground truth set. All right. If it doesn't match, we mark it as negative. All right. So then we plot a point on precision recall curve. All right, so we have a precision and recall. I hope you know what is precision and recall, right? So from this, we calculate precision for this just one example, right? So we are evaluating the first one. So the precision will be 1 divided by 1. It will be precision 100. And recall is 1/3, right? Because we have these 3 ground truth box, and then we already detected 1. So which means that the recall is 1/3. We already retrieved that one ground truth. All right. And then we keep repeating this with the next one, with the second highest score. For example, this one, 0.95. And then we do the same thing to see whether it match with any other ground truth or not. And then the IOU between the two is greater than 0.5 or not. All right. And then we plot another point on the precision recall. So precisions, we are testing 2, and then we get that correctly 2. So it's 2 by 2, it's still 100 here for this point. And then it got recall is 2 divided by 3, which means that we already retrieved 2 out of these 3 ground truth. So we get this recall is 0.67. We keep repeating again, right? We keep repeating again. Oops. We keep repeating for the next one, right? So the next, the third highest score, and then we try to match it with the ground truth. So now it didn't match any ground truth, right? It didn't match any ground truth. So we plot that. The precision is dropping because we have XMI 3, but we get only 2 positive. So it will be 2 divided by 3. And the recall is still the same value, right? Because we already retrieved 2 out of 3 ground truth. And we plot this, the third point over here. And then we repeat it again, right? For this point, it seems to be a negative one. So we plot it here. So our precisions get lower because out of these 4 sample, we examine 4 and then we got 2 positive, so that the precision will be 0.5, right? We plot it again, and we repeat it again with this one. So luckily, this one is matched with the last ground truth, and then it has overlapping area greater than 0.5. So we plot it in here, and then after that, we calculate, right? We calculate this area. All right, for this dark category. So we can, after we calculate this area, for example, we get the area under the curve of 0.86. So that's represent the average precisions of the dark category. And for the cat category, we keep repeating the same process, all right, until we get all the average precision for all category in our data set. All right, so then after that, we will sum everything up for all category. For example, we have these 3 categories. We can find the average precisions for each category. We sum them all up, divide them, find the mean out of all these categories. For example, we have these 3 categories with this average precisions. So the mean average precisions of the models, of our models, is equal to 0.7, all right? And the add 0.5 here is the overlapping area that we are testing. So if you look at this one, it's 0.5 IOU that we are using that as a threshold to measure the overlapping between the predicted and the ground truth. So if we want this to be higher, so we can have many metrics. For example, MAP at 0.5, MAP at 0.6, at MAP at 0.9, something like that. So that's what it means. See, the mean average at what is the IOU that we are using as a threshold, right? So that's how you evaluate the model performance for object detections. All right, does it clear? Is it clear how we evaluating the performance of the object detection models?
Let me thinking again. So most likely we calculate the precision and recall based on the ground truth. We have only 3 boxes right here, and we have the our model detection on the above with 5 results. So we gonna calculate the precision and the recall.
Yeah.
So we just matching each box with the current one based on the threshold 0.5 IOU. If match, yes, I mean the precision recall is the straightforward formula. I think it's from machine learning class. So we just compare the total numbers and then over this one based on the threshold 0.5, which means that we can adjust this threshold, right?
Yeah, we can adjust this threshold.
Yeah, same like K-mean classification problem when we calculate this number.
Yeah, so it will reflect here what is the threshold that you are using for the overlapping area between the predicted and the ground truth. For example, here will be using 0.5 as the IOU, the threshold.
Okay. So all right. So almost this, I mean the concept still the same, but the different now is the box object between and the threshold is the IOU.
Yeah.
Because in the ML class is the threshold normally is the probability, I think.
Yeah.
Okay, thank you.
Okay. Any other questions? All right. If not, let me move on. So what is the problem with this method is that as you can see, we have to run a region proposal method, right? We have to run a proposal method, and then from that we get roughly about 2,000 regions, right? So we have to feed in those 2,000 into the CNN networks. So, and then it will process for each 2,000 region for each image. So that could be very slow, right? By using these methods. Okay. So the solution is that instead of just run the region proposal first before feeding each region into the CNN, we just swap the process. So the solution is to swap, like to warping the image before we perform the region proposal. So what does that mean? So that's bring us to a fast RCNN. So instead of just finding the region first and then pass it through the CNN, so we pass the image into CNN first. All right, we swap the sequence. So this CNN could be, for example, AlexNet, VGG, ResNet, something like that. So we run the whole image through this CORDNet first. And then what we end up here, we end up with the image features or the feature maps, right? So this is what we got. All right. And then after that, we run a proposal method on this image feature instead of the raw image. We run the proposal method on these image features. Okay. And then we crop that image features and resize it, and then pass it into another regions, another CNN. All right, we pass that into another CNN so that it can predict categories, and it also can predict the box transform for each region. So the output is the same. The medium, we just swap the sequence. All right. So this network, a per region network, could be a very small, very lightweight network, right? It could be a linear model, something like that, right? And then this CORDNet could be like AlexNet, ResNet, VGG, something like that. So yeah, it could save this could save works for like overlapping region proposal. All right. So for example, if we are using AlexNet, we could probably use these first 5 layers as a backbone network here. And then at the end of this, we're going to get the image features. And then we are going to perform the proposal method from here to extract regions, and then pass these regions into these two fully connected layers. It is nothing but a linear layer, right? It pass this into this fully connected layer so that we can get the predictions of the class and the bounding box of each objects. Or if you use ResNet, you could probably use the first 3-4 ResNet blocks from here as a backbone, and then use for the last ResNet plus a fully connected layers here as the per region network to predict a class and the bounding box of each object within the image. All right. So this is how we do the fast RCNN, just swapping the order. Okay. So the thing that left from here, that left to answer from here is that so as we're training the models, right? The thing that we need to do is we need to perform the parameters update, right? After the model make a predictions, we calculate the loss, and then we back propagate in order to adjust the parameters of the models, right? So to do that, when we perform a back propagations, what it does, there's a partial derivative that when you perform a back propagation. So which means that the thing that we are making a crop here or running a region proposal here. So these operations need to be differentiable. All right, it needs to be differentiable, which means that we can the back propagations or the gradient can pass through this operation, this region proposal method. All right. So the question is how to crop the features so that it is being differentiable. All right. So let's recall the concept of receptive field. All right. For example, here we have the input image of 8x8 and the output will be 8x8. Okay. So for every positions in the output features, so after we apply, for example, we pass this image through the COF layers, which with 3x3 filters, strike 1, padding 1. All right. So we pass this in, we got these image features. We got these image features, right? So every positions in the output features, all right, in the output features or feature maps, it depends on a 3x3 receptive field. So because we are using a 3x3 filters here. So if you look at these positions, right? So these positions, the receptive field of these elements or these positions in the output is depend on this 3x3 receptive field in the input, right? And also, if we pass this image through two COF layers, right? So which means that every positions in the output image or the feature maps depends on a 5x5 receptive field in the input. Right? Do you remember why it's if we pass this image of 8x8 with filter 3x3 and then with filter 3x3? So the receptive field of this feature maps is 5x5 in the input, right? Do you guys remember?
Yeah, represent the 5x5 of the original input.
Mm-hmm.
So the next layer would be the whole image, I think, if I remember well.
So let me recall, right? If you have this input image and then this is your COF, you pass this is your filter, right? This is your filter, all right? And then you're sliding this over, right? So let's say that this 3x3, okay? So, and then this is your output feature map. This is your feature maps, all right? This one elements over here, this one elements is the resultant of these filters 3x3, all right? Dot product with this area 3x3, all right? 3x3 over here. So the receptive field of this is this one, okay? And then if you pass this feature maps to another COF layers, all right, then you get here another COF layers. So this element, if you look at this element is the result of this 3 by 3 in the previous layer, right? In the previous layer. All right. So this one is the result of this. And then if you look at this entire area, it's correspond to 5 by 5 in the image. It's a result of this 5 by 5. Every image in here, every element of this area correspond to this 5 by 5 area in the input. So that's what we call the receptive field of this with respect to the input is 5 by 5. Okay. So I hope you remember from yesterday.
Yeah. I still confused yesterday, so I look for it a little bit and now remember.
So if you're moving 1 unit in the output space, so it's the receptive field is also moving by 1. So it's the same thing, right? So that's the receptive field. So what we want to discuss in here is that we want to say that there is a correspondence, right? There's a correspondence between the coordinate system of the input and the coordinate system of the output, right? There's a correspondence. It's either you move anywhere from within the output, so which means that you're also moving within the input as well. So there's a correspondence between the coordinate of the two, because when you are performing convolution, you are mapping features from original input features to the feature map of the first layer, and then you map into another feature space. All right. So this feature space, they have a correspondence between the coordinates of those, right? So let's say, for example, here we have these positions in this input image, and then the resulted in the output image will be, we can calculate that, right? Because we can transform from one coordinate to another coordinate, right? Let's say that in this example, the input has the resolutions of 8 by 8, and then if the resolutions of this output or the feature map also 8 by 8, so it will corresponding 1 by 1. So which means that these locations, we can map it directly to this location, and that this location we can map directly to this location, right? Because we want to find locations. So the thing or the objective that we want to do here is that we are having a feature maps, right? After we run the entire image, through a CNN network here. So what you get out from this network is a feature maps, right? It's a feature maps. So that next, what you want to do is that you want to run a region proposal method. All right, you want to run a region proposal method on these feature maps. All right, which means that you want to extract positions within a feature maps. Where is the locations of an interesting features? All right. So instead of doing this in the original image, you are going to do it in the feature map instead. So that's why we need to find the transformations of the positions between the two. All right. So if we keep decreasing the resolutions of these feature maps, we can still translate. All right, we can still translate the coordinates from the input image to the feature maps coordinate. All right. And also, let's say that this is 4 by 4, from 8 by 8 to 4 by 4 to 2 by 2. We still be able to find the locations of one point in input in the output. All right, so that we can use this idea to project a bounding box between input image and a feature map. So that's the concept why we need to understand this one, right? Because we need to project a bounding box from this input to the feature maps. All right. So remember that what fast RCNN is doing is that we first pass this raw image, right? Pass this raw image through this CNN first, and then we're gonna get the image features, or we call feature maps or activation maps, whatsoever. And then after that, we are going to run the region proposal on this feature map instead of the raw image, right? So, but we know the ground truth, right? We have the ground truth. This is our ground truth. Whoops. So this is our ground truth. We want to map our ground truth to the feature maps. So what we have to do is we have to project. We have to project a proposals onto a feature maps, right? We need to map that onto a feature maps, right? And then that's how we are going to borrow the idea from that previous slides. So the first thing we need to do is that we are projecting proposals onto a features in this area, right? So when you're projecting this box from the input coordinate into the image features coordinate, that it might not perfectly align with the grid over here, right? So what you do next is that you snap it to the grid. All right, you snap it to the grid. You snap it to the grid. And then what you're going to do next is that you're dividing this area into a 2x2 grid. All right, it could be equal or unequal. It's okay. All right, you're trying to divide them into a 2x2 and perform a max pooling within this area. So you will end up with a 2x2 of this to represent this entire regions. All right. So you keep doing that for every regions that is you got from a region proposal. All right. So the problem with this method is that a slight misalignment between this sub-region, or because you're snapping into a grid, right? So a slight misalignment due to a snap here can cause a very different size of sub-regions. So to solve that, so we don't snap it, right? To solve that, we don't snap it. We just project it. And then what we are going to do is that we are going to divide this area into a equal size sub area first, right? And then we sample a point in each sub-regions, right? By using, for example, a bilinear interpolations. You sample the point over here, all right? And then you are going to do a bilinear interpolations. Bilinear interpolation, for example, for this point, you want to find a value. You want to find a value for this point. So what you can do is you can use a bilinear interpolations by borrowing the value from each of its neighbor, right? So for example, for this point, to get a value for this green point, you are calculating a bilinear interpolations. For example, from this point, you're calculating in x directions and y direction. So this is what you got. And then you're calculating bilinear interpolation between this point and this point. So this is what you get. All right, you keep doing that with this point, green point and red point. So you keep doing with all the four neighbors, and then you will up with the final value for this one. You sum them up, you're gonna get the final value for this point. So you keep doing this for every point in the sub-regions. All right, and then you take a max pooling from that. You take a max pooling within this image, within these sub-regions. All right, you're gonna get a region features. So this is what we call a region features. So from there you get a cropped image. You get a cropped image. from here, right? You get a cropped image, and then you pass that crop image into another lightweight CNN, and then the model will predict a class and the bounding box for you. All right. So if we compare the difference between the fast and the first versions of RCNN, or we call it slow RCNN, so we can see the difference that is we just swapping the regions proposal methods between the two, right? So that's the difference between these two versions. So if we compare the performance of fast RCNN and slow RCNN, so you can see that the fast RCNNs, it is faster. It is 10 times, almost 10 times faster than the RCNN in the training period. And when a testing period, it's improved very much, right? For example, if you look at the test time, which include a region proposal method. So the RCNN took 45 seconds, but for fast RCNN, it's just 2.3 seconds. All right. So the problem here is that if you look at the test time of fast RCNN, all right, the runtime is mainly dominated by a region proposal, right? If you look at the time that it took that include a region proposal method and exclude the region proposal method, it just like 10 times, right? Just like 10 times. So, which means that there's a room for us to improve here, right? There's a room for us to improve here. There's a problem there with using a region proposal methods. All right. So we can say that a region proposal methods, it is computed heuristically by using a method, for example, selective search, right? Selective search algorithm. So what if instead of just using a heuristic method or a heuristic algorithm like selective search, the question is, can we use a CNN to learn how to get a region proposal instead of just heuristic search? So that's bring us to a faster RCNNs, which is a learnable region proposal. All right. So we will see how can we eliminate a heuristic selective search algorithm to extract a region of our interest. And then instead of that, we are going to use a CNN to learn how to propose a regions that should be the region of interest. All right, so next class, we are going to learn about the faster RCNN. All right, so any questions about fast RCNN, slow RCNN, and then how the region proposal works?
Sorry, doctor, I got lost in the, still confused in the reasons RY. Can you this thing?
Which one?
The reason of interest.
Region of interest?
Yeah, it's the selective search, the box, right?
Yeah.
Which means that the box will be, let me come up with this.
This one.
This one. Okay.
So this is what we call region of interest, or the region proposal methods.
So firstly, they search greatly. I mean all the reason. Right now they use the this kind of selective search.
Selective search method. So basically there are many ways you can do a selective search. For example, you can use a technique like SIF that we already learned, right? SIF can detect any features, right? So for example, you probably use SIF to find regions or to find a subset within the image. Right? So probably, for example, there could be, if you use SIF, right? If you use SIF, there could be a SIF over here, one of them, a SIP over here that has a side of this, and then another SIP of here that have side of this, another SIP features that have a side of this. So let's say that you are setting a threshold of a SIP with magnitude of let's say 0.5, something like that, right? So this area of the circle, so then you convert the circle into a rectangle, right? So you probably say that this would be probably a region of interest, and then this probably would be another region of interest. So that is the region proposal. That's how the selective search is working.
Okay, clear.
Yeah, so that's how we got from here to here. Yeah. All right. Any other questions? All right. If not, I think this is it for today's class. And later today, I'll post this instructions for the final project in Teal, so you can check that out later. Make sure that you understand the instructions and understand how to make a report, right? And then submit a report. So the deadline for the reports will be on July 27, if I remember correctly. All right. And next week, there's no class. And then I will see you in Hanoi on July 12th and 13th. Right. So for the final exam, I will tell you in that week which topics will include in the final. Right. So any other questions? So if not, I'll see you in Hanoi. Right. This is it for today.
Okay.
Bye bye.